Hi there, welcome to another tutorial on moles. And in this tutorial we're going to be going through calculations involving solutions. And this is quite often a tripping point for many pupils because it brings together a couple of different types of mathematical concepts which are very simple but together can cause a little bit of confusion. So we're going to try and clear that up today. So first of all, let's just get used to this definition of what a solution is. A solution is something which is made by dissolving a solute, so a solid solute, into a solvent. So for example, putting sodium chloride into water and dissolving it up, and that is a solution. So solutions are always clear, they're never cloudy. Cloudy solutions have got a precipitate or something in them which hasn't dissolved. So solutions are clear. Okay, so that's the first thing, sort of definition to get past. Now, solutions in chemistry have two different units, and these are displayed here for you. So the units of concentration then are either displayed more commonly as moles per decimeter cubed, and we'll come to what that means in a minute, or grams per decimeter cubed. So it can be expressed in either way. It's important to know the difference between the two. In fact, this one here, moles per decimeter cubed, this is also called the molarity of something. Molarity. And the units of molarity are moles with the capital or the capital M. That's molarity. So this is what you'll commonly see on many solutions and things that you'll use. You'll see, for example, you might see a solution of sodium hydroxide or something like that, which has this on the bottle, so 0.1, and then this is the molarity of it. Okay. Now let's come back to this dm cubed thing. Now this is decimeters cubed. Now 1 decimeter cubed is equal to 1,000 centimeters cubed. So in order to sort of go between the two of these then, to convert something into decimeters cubed, you divide by 1,000. So quite often examiners will give you something, a volume in centimeters cubed. You've got to convert that into decimeters cubed, and that's very important. So converting the units is very important, so make sure that you're in the right units before you start any of these calculations. Now let's bring back in our old friend, the calculation triangle, the Molar calculation triangle we used before in previous stuff. So for example, you've got mass over moles and relative formula mass or molecular mass, also known as the molar mass, as we know. So we're very much used to this triangle. Now we can use this triangle now to go between these here. So for example, if we're going this way, so we're going from moles per decimeter cubed to grams per decimeter cubed, if you want to find out what it is in grams per decimeter cubed, we can use the same triangle to help us out here. So we know what the if we know what it is in moles per decimeter cubed, and we want to know what it is in in grams per decimeter cubed, we can do the moles times the MR, or times the relative formula mass. So if you're going that way, and if you're going the other way, so if you're going from grams per decimeter cubed to moles per decimeter cubed, you do the opposite, so you divide by the relative formula mass of the molecule. So depending on what the examiner wants and what you have, make sure that you can convert between those two things. So you've got converting units, knowing that this is molarity, and being able to convert between moles per decimeter cubed and grams per decimeter cubed. Now we're going to bring in another very useful formula triangle. This is going to be a second one we're going to use in conjunction to the first one. And this one now brings in this idea of moles with the volume and the concentration of something. Remember, these are the units of concentration up here. So we can use this triangle to help us answer some questions. But it's very, very important to recognize that there is a link between these two triangles, because we've got moles here and we've got moles over here. So if we are given, for example, the volume and concentration of something, we can find out how many moles of it there are. And then we can using that, we can go across to here, and we can, by using its relative formula mass, we can find out the mass of it. So knowing that these two link up is very important. So what I would suggest you do is, whenever you approach a question like this, you want to be drawing out these triangles before you start. Okay, and that's what we're going to do. So we're going to have a look at some examples now, and we've got this to help us with each of these ones. So this is the first one we're going to look at here then. We've got, and I put up our triangles up here to help us out a little bit. So the example here then is, and what I'm going to do is I'm going to annotate this as I go through, and this is what you want to be getting into the habit of doing whilst you're doing these questions. So we're going to pick out the key things we need and exclude everything else we need. So it says what mass of barium sulfate, that's going to be quite important to us, what mass of barium sulfate would be produced by adding excess, and here's barium sulfate, so barium sulfate is here, so that's that, would be produced by adding excess barium chloride, and there's our barium chloride, to 20 centimeters cubed of copper 2 sulfate solution of concentration 0.1 moles per decimeter cubed. So we've got a couple of different values here, so let's just filter through this for a second. So we want to know what mass of barium sulfate we produced by adding this to 20 centimeters cubed of copper 2 sulfate solution of concentration 0.1 moles per decimeter cubed. So this is our key information. So now I've sort of picked out those key bits there. What I'm going to do now is I'm going to annotate my equation. And here's our copper sulfate as well. So these are the two things we're really interested in. Okay, so we've got a volume here of this then of 20 0.0 centimeters cubed of this, and we also know its concentration, which is 0.1 moles per decimeter cubed. So make sure you're aware with these units now that we're using. And we want to find out what the mass of barium sulfate is going to be here. So we've annotated our equation now with the information we need, and that's probably one of the most important steps. Okay, next thing I'm going to do, we have got a volume here, but we've got it in centimeters cubed, and we want that in decimeters cubed. So I'm going to convert that to decimeters cubed. So 20 centimeters cubed is the same as we divide that by 1,000 to give it to us in decimeters cubed. So that's going to be 0.02 decimeters cubed. Now that's really important that we've got our units right. So we've annotated our equation, we've converted our units, we're ready to roll. So you've got to be quite savvy here and realize that we've got, in terms of a molar relationship, we've got 1 mole of this reacting with 1 mole of, reacting to give 1 mole of that. So we've got a ratio of 1 to 1. So if we can find out how many moles of copper sulfate we've got, we can find out how many moles of this we've got and go over. So we're going to start off with our right-hand triangle here then, because we have got volume and we've got concentration. Remember the volume's over here. So then, so the moles of copper sulfate, CuSO4, is going to equal the volume times the concentration. And we know that the volume is 0.02 decimeters cubed, and we know the concentration is 0.1, so we can do that. So then in that case we've got 0.02 moles of copper sulfate. Okay, so those are our units there, moles of copper sulfate. Now, if we've got a ratio of 1 to 1, that must mean that we've also got 0.02 moles of barium sulfate, because it's in a 1 to 1 ratio. So that's our bridge that's going over there. Okay, so that's going to also equal the moles of barium sulfate. Now, if we know how many moles, we're going over to this other triangle here, we've made the link over here, we know how many moles of it there are, and we can work out the formula mass of it by using the information here, and you can find out the mass. So now then, we're actually going to answer the question. So the mass of barium sulfate, BaSO4, is going to be equal to moles, how many moles of it we've got, times by the MR, the relative formula mass. We know that there's 0.02 moles because there's a ratio of 1 to 1 there. We can work out the formula mass of barium sulfate by using the information we're given, so 137, 32, and 16 for oxygen. So the relative formula mass for this is going to be 233.1 if you work it out. And then you times those out and you get 0.4662 grams of barium sulfate. So make sure now that you've got those units. Okay, it's in grams. So we've answered our question there. We've linked up the two triangles. Okay, let's have a look at another question then. So this one's asking us, what is the mass of, I'm going to highlight as before, so what's the maximum mass of calcium carbonate? Calcium carbonate, so we're interested in this one, calcium carbonate, which will react with 25 centimeters cubed, that's a volume, of 2 moles per decimeter cubed, that's a concentration, hydrochloric acid. And here's our hydrochloric acid. Okay, so that's all we're interested in. You can kind of forget about the rest, to be honest, for now. Okay, so let's pick out the key information that we've got then. So we have got, we want to find out the mass of this. Okay, we know that there are 25, oop, that looks like an 8, but that's meant to be a 5.0 centimeters cubed of this, that's a volume, and we also got 2.00 moles per decimeter cubed of this as well. So we've got that information there. So we've answered with all the information we've got. We need to make sure that we convert this into decimeters cubed. So remember, 25 divided by 1,000 to give it to us in decimeters cubed, which is going to be 0.025 moles. Sorry, decimeters cubed. Good grief. Decimeters cubed. Okay, so that's the volume that we're going to be using for that then. Right then, so let's have a look at our triangle. We know the volume of hydrochloric acid. Oh, we didn't do the molar ratios. So we've got 1 mole of this reacting with 2 moles of this. Now that's really important. There's our 2 there. Like 2 moles of that's going to come in important in a minute. So let's have a look at this then. We've got a volume then, so we know what volume it is. So we can work out the moles now then of, let's go blue because I'm like in blue. Moles of HCl. HCl is going to be equal to, like we said, the volume times the concentration. We know the volume is 0.025. Remember, we're using the decimeters cubed version of it. Times by 2.0, which is the concentration, which gives us 0.05 moles. Okay, and that's our units. So remember, we're using our bridge then. So if we've got 1 mole of hydrochloric acid, sorry, 2 moles of hydrochloric acid and 1 mole of calcium carbonate. So we've got a half the number of moles then for this. So the moles of calcium carbonate, CaCO3, is going to be 0.05 divided, oh man, why do my face keep coming out like 8? Divided by 2, because that's to find out the moles of it. So we're going to have then 0.025 moles for that. So obviously we're going to use that now when we're working out with calcium carbonate. So we know how many moles of it we've got. We can find out the molecular mass. We can find out the mass. So again, let's go with orange. So we know how many moles. So we're trying to find the mass. The mass of calcium carbonate. We've made our link here now. Calcium carbonate is going to be the moles times by the relative formula mass, the MR, which is going to be 0.025 times by, when you work it out, you get 100.1, which equals 2.5025 grams. And that is the maximum mass of calcium carbonate, which will react with that then. Now, in addition to the stuff we've done already, I wanted to go through this example just because examiners really like to throw loads of information at you like this. So you've got a paragraph of information to sift through and 2 equations which makes you think, oh crap, what am I doing? And I'm going to show you now that it's not as difficult as it might look. Don't be scared off by what you see before you've even had a read of it. Okay, so we're going to read through it, we're going to pick out the information that's important to us. That's really important. So, a student set out then to make some copper 2 oxide from copper 2 sulfate. He took 20 centimeters cubed, so that's a volume, of 0.4 moles per decimeter cubed, that's a concentration, copper 2 sulfate solution, copper 2 sulfate, there's my copper sulfate, added an excess of sodium hydroxide to give a precipitate of copper 2 hydroxide, and then boiled the mixture to convert the copper 2 hydroxide into copper 2 oxide. Now all that is pointless to us, because that doesn't have anything to do with what we're doing necessarily. Okay? It's all it's doing is describing what's happening in the reaction. But at the moment, none of that is relevant to our calculation. Now what he wants to know is what's the maximum mass of copper oxide, there's my copper oxide, that he could obtain. So we're going to do the same step as we've done before. We've broken down this entire paragraph here into a couple of little bits. So first thing I'm going to do is I'm going to annotate my equation. So I've got 20 centimeters cubed then of this. So 20 centimeters cubed. Remember, we're going to have to turn that into decimeters cubed in a minute. And we've got 0.40 moles per decimeter cubed of that, which is our concentration. So we've got 2 bits of information about that. And we want to find out the mass of copper oxide. Oop. Okay, so we're actually broken this down into much easier. Now remember, if you look at this, for copper sulfate, let's go through the molar ratios of this. You've got 1 mole of copper sulfate reacting to give 1 mole of copper hydroxide there. And we've also got 1 mole of copper hydroxide here reacting to give 1 mole of copper oxide. So we're going from here over to here is 1 mole, and then here to here is 1 mole as well. So if we've got 1 mole of this, that means it'll be the same as 1 mole of this. So that makes our lives a lot easier now. I'm going to change this over here into decimeters cubed. So 20 centimeters cubed divided by 1,000 to put it into decimeters cubed. It's going to give us 0.02 decimeters cubed. There we go. Now we are ready to go. We've done all the hard bits, picking up the information, sifting through stuff. Right, easy peasy now. So we've got the volume, we've got the concentration of this, so we can work out how many moles we've got. So let's go blue again. Moles of copper sulfate, CuSO4, is going to be equal to the volume times the concentration. Again, exactly the same stuff as we just doing, which is going to be 0.02 times by 0.4, which is going to equal 0.008 moles. Okay, so don't think, oh, I'm too smart to put out the steps, okay, because you'll mess something up. So stick with the this way of doing it. So we've got a ratio then of 1 to 1. So that's going to be the same number of moles of copper oxide. It's moles of copper oxide. So then, again, we know the moles, we can work at the MR. It's so easy, it's so easy. So then the mass of copper oxide, CuO, is going to be equal to the moles, which we know, times by the MR. And we know that this is not the same as the other one, so because it's in a ratio of 1 to 1, so 0.008 times by 79.5, because I have gone ahead and worked out the molecular mass of copper oxide, and that gives us 0.636 grams of copper oxide. Hurrah! Simple. Okay, cool. So the key is you can use these little triangles here to help you out anything. Steps are identify what you've got, okay, so sift through the information, annotate the equations, okay, find out the molar ratios, make sure that your units are all in decimeters cubed, so make sure you've made that conversion there. Make sure if it's asking for something in moles, if you're, for example, it's asking you to work out the concentration, make sure that it's in moles per decimeter cubed if that's what it's asking for. If it wants it in grams per decimeter cubed, make sure you put it in grams per decimeter cubed by using the conversion in the first bit we talked through. Okay, so these same steps just employ the same steps, like 1, 2, 3 steps of actual calculations, and we've done these bits here to annotate our equation. Simple! Okay, hope that helped.